not going to do it in deference to doing Bloom filters, which I think is probably a little bit more useful. I don't know, maybe usefulness is all very relative, but anyway, this is a data structure that is randomized, and well, anyway, let's see how it works. Yeah? Okay, so let's do that. The idea is that you have a very large disk-based data structure like a database, okay, and like most databases, we haven't spent a lot of time with databases, don't worry, it's basically like a set of keys, and the keys could be anything, okay, so it could be your name. It's not a people-based database, so that's not the way SFU does it, right? SFU has keys by your student ID number, that's your unique identifying mark, you know, because somebody might have the same name as you. Okay? That's been known to happen. Anyway, these things are usually too large to fit in main memory, so they reside on disk. And you make queries, sometimes from a long distance. Sometimes it's the distance is from you know, across campus, that would be a long distance, or even further away, like across the world, across the internet, World Wide Web type of thing. And you can try to save time by maybe caching the essential bits of the key in a smaller table. Okay, so one idea is to hash all the keys into something smaller. Say it is your name, right? Those are strings that are very long. In some cases, you know, let's say they're at most 30-odd characters. That's a lot of bytes, right? That's a lot of bytes. So what you could do is you could hash the strings and make them into, say, 32-bit integers and store the integers instead. Okay, and this is how hashing works, and I don't want to go over what a hash table does or how it functions, but basically you take advantage of the fact that you can, you know, identify something using a smaller fingerprint, okay, a smaller number of bits, to save some space. Okay, so you know you're trading a little bit of you know, you're trading a little bit of lookup time. Like you have to look things up in the hash table, and then if it happens that there's a key that matches or a hash value that matches, then you'll have to go to disk. So there's like an extra step involved, but you can save some space. Okay, and oftentimes if the hash table says no, you don't even have to search the disk because no is no, right? If the key or the hash key is not in your hash table, you can actually avoid a disk access altogether. Anyway, Bloom filters are sort of an extension of like a hash table. They sort of behave in a similar way. There is some randomized thing, but it's even thinner than a hash table. Okay, and the trade-off that you make is you gain some space. Okay, so you save some space at the expense of some error. And it might seem like accessing a data structure, like a set data structure, should be error tolerant, like you shouldn't have any error at all. But it actually turns out that it's not so bad. Okay, so here's how it works. If you ask the Bloom filter, is it in the set, it will 100% say no if the thing is not in there. Okay, so the key is not in there, 100% says no, so there's no false negatives. But occasionally, and you can tune this, okay, but I'll just say 1%, so it's fairly rare, there is a small chance it will say yes with a, when it's not actually in the set. Okay, so you can avoid some disk accesses by doing this. Okay, so occasionally 1% of the time you end up going to disk when you didn't have to, but that's probably better than having to go to the disk all the time. Okay, some applications before we get into how this thing actually works. And there are a whole, you know, there's a big Wikipedia page you can read about a whole bunch of these things. I listed 3. Maybe the one I should focus on is search engines. You can read about the other ones. So search engines, say Chrome, for example, pretty popular, has a list of malicious websites, attack websites, built into it, so that if you try to access an attack website, it will try to save the day, right? Okay, warn you very strongly, you know, do you know this is an attack website before it loads the page, and it will ask you, are you sure, etc. Okay, so the list is pretty long, like it's something on the order of millions of URLs. The URLs themselves aren't very long, okay, but each one of them is a string. So you can imagine there's a million strings, and you multiply that by whatever the average size of a URL is. We're talking like several megabytes of information, like just say 30 megs or something. And that might not be something that you want to hold in main memory. Maybe memory is cheap, but maybe you don't want to hold that in main memory and search it every single time. Okay, so instead, what they do is they hand a Bloom filter over. Okay, so this Bloom filter is way cheaper. It's about a meg, and that's probably tolerable. And this thing, you know, anytime it gets a URL, it hashes it, okay, accesses the Bloom filter, and the Bloom filter will say no, probably most of the time. Okay, occasionally it will say yes, which means you either are going to an attack website, or it erroneously said yes, right? You're going to a fine site, it's perfectly innocent, and it will go and search the entire thing off-site to make sure to, you know, that you're actually going to an attack site. Okay, so that's when it will pay the extra cost, and it will do it by, you know, normally it accesses the database off the internet because, you know, Google likes to keep these things updated off-site. Okay, so a lot of the time it's going to say no. Okay, so this is a sort of a characteristic of when a Bloom filter is going to be useful. Okay, so the payoff are highest if no is the most common response. Okay, and probably for most users it is. Maybe you go to attack websites all the time, but probably not, right? Okay, so usually it is. Maybe I'll give it one more example. It's not listed here. Google also has a large database, well, spreadsheet really. Okay, so it's a spreadsheet of cells. It's like huge. Okay, it's like 1,000,000 by 1,000,000. Okay, and most of it's empty. Okay, so the way they store this thing is by only storing the active cells. Okay, so they keep a list of which cells are active, and that list gets put into a Bloom filter. Okay, so anytime you want to query is the cell empty or not? Chances are it's empty, so it will say is it occupied? Chances are it will say no. Okay, and it will say no, and it'll never have a false negative. And if it does have a false positive, that's when it goes and hits the disk. Okay, so yeah. You can read about the other ones, okay, so there's caching, and these are basically, it's another level of cache, but it has a little bit of error built into it, blockchain names in a database that are easier to find. Okay, most of the time, if it says no, that's the big payoff. Okay, let's see how it works. Okay, 2 pages of strategy. Okay, first thing, the data structure itself is just a bit vector. Okay, so if you've never seen a bit vector before, it is an array of zeros and ones, that's it. Okay, so you just implement it as an array of bits, m bits. And there are k hash functions, and each of them maps between 0 and minus 1. Okay, so 0 indexed bit vector and k hash functions that map to some of these bits in here. Okay, so if you have n keys, the way you set up your Bloom filter is you first select m and k to be big enough so that it has some certain properties and satisfies your error tolerance, which we'll see later. And for each key, you put it into the Bloom filter by setting each of these hash functions, whatever the key hashes to 1. Okay, so those together, those k hash values are called as fingerprints. So here we have an example of here for the key 42, and k is 4 in this example. So its hash values on hash 1 is 5, 8, 1, and 0 for hash 4. So anywhere that those values occur, okay, so those array indices will be set to 1. Okay, and if some other key has already set it to 1, that's okay. Okay, so here we're only going for, I guess if we think of this as balls and bins, and we're going to think of it as balls and bins in a moment, we only care if each bin is empty or not empty, basically. Okay, so has part of a fingerprint touched a bin. Okay, so this is very much like balls and bins from before, and we have our analysis slide a little later that actually says balls and bins. Okay, with how many balls do we have? Well, there are n keys, and they generate k balls per key, right? Because they're k hash values per fingerprint, so there are going to be kn balls that get mapped into m bins. Okay, so these are the hash values. Okay, so all the fingerprints are there, and this m bins are the bits in the bit vector. And I saw your hand earlier, but I'm just going to do the next slide, and then if you still have a question, we'll take care of it then. Okay, so just hang tight. Okay, so this is how we set up the Bloom filter. We fingerprint all n keys, and we basically OR all of the results into these bins. Now, some of these bit vector things are going to be 0, and some of them are going to be 1. So the test that we go through to see if we query the database is x in the set is we find the fingerprint for x, and we check the bit vector. Okay, so I've repeated the example up above. Okay, so if x is in the set, we compute all the keys, all the parts of the fingerprint, and we check to see if all of them are 1. Now, if any one of them is 0, then it can't be in the set, right? Because if it was in the set, all of them would have been set, right? So it can't be there, so that's good. So no false negatives are possible, because one of them is 0. But it's possible that all the other keys that are actually in the set sort of randomly set all of these k values to 1, sort of by fluke, if you will. Okay, but it's not very probable that happened. Okay, it's very likely that x is in the set, but there is a possibility that all k values are incorrectly set. Okay, it's just a coincidence. Okay, either way, if it returns yes, you need to actually verify that it's in the set, and that's the expensive operation where you go ask the internet or hit the disk. Now, what's the parameter here, right? This is all sounding very familiar. We have a k things that we check to be 1 or 0. And if you just imagine that these were 1 or 0 with a probability of a half, then this is like tossing a coin k times. Okay, it's not quite that way, but just from a simplistic point of view, if the probability was even money, okay, so the probability each bit was 0 or 1 was around half, then x triggers a false positive if all of those things end up being 1, sort of by accident, right? So, so when all k of its bits, of its fingerprint, are 1s, and the simplistic point of view, and I realize I'm making it more simplistic. I can't do the full analysis, but it sort of feels like it's going to be half times a half times a half times a half k times over, which is 1 over 2 to the k. Okay, so that's how likely it is. And just in general, and we're going to see this a little bit later, this is how you pick k. All right. So whatever your error tolerance is, I don't know. I don't know how error tolerant your system is or how error tolerant you are, but you would pick k according to that. Okay. So pick k according to your error tolerance. Okay. So for example, if k is equal to 7, then your probability of a false positive is going to be roughly 1 over 2 to the 7. That's 1 over 128. This is slightly less than 1%. Okay, so if 1% is good enough, you'll pick k equals 7. Okay, so let me just recap. All right, you prepare your data structure according to whatever keys you have. You have k independent hash functions. Okay, so you run all your keys through these hash functions. You set for 1 each bit where it touches in the bit vector. Some of them are going to overlap, and that's okay. Anyway, therefore, anything that's in the set is going to trigger a yes. Okay, anything that's not in the set is anything that's not in the set is going to trigger a no. Anything that's in the set is going to trigger a yes. But it's possible that there's something that's not in the set that it still triggers a yes. Okay, because they might all be 1. Okay, so that's where the false positive comes from, and you're going to have to search the database anyway. Right? It says yes, you wanted the data, so you go to the database. Okay, that's the scheme. Before we go on to the analysis, I just want to make sure you understand how it all is going down. Any questions about this data structure, how it operates? Okay, so you asked, are there k items in the set? The set itself has n items, okay? And each of those n items generates a fingerprint, which will generate k1s, okay? And those k1s are stored in the bit vector in some pattern, right? So I've shown here for 42, it's going to put in 4 1s in those locations, okay? So you can imagine each key is going to put 4 1s in there, 4 1s somewhere. They might overlap with some of the other ones. That's okay. Is that clear? So n is the number of keys. K is the number of hash functions that generates a fingerprint, so that's the size of each fingerprint, and M is the size of the data, of the filter. Do you still have your question, or is it sorted out? Okay. Other questions? Thanks for that. Is it good? Okay. Normally I have a picture of the guy who invented this. It's named after the guy who invented it. It's Bloom. If you go to the internet or you ask, one of your textbooks actually talks sort of affectionately about Bloom, in that they don't know who Bloom is. They have a name, they know who he worked for, they have the paper where he developed a Bloom filter, but they don't know who he is, where he grew up, where he studied, anything. There's no information, there's no picture, nothing, a bit of a mystery. So anyway, maybe you can solve the problem for us, that'd be great. Anyway, okay, so as I mentioned, this is like a balls and bins problem, so we're going to revisit this a little bit, where there are k n balls and m bins. I'll tie this back into the Bloom filter once we've answered the following question. Okay, so let xi be the event that bin I is non-empty. Okay, one specific bin. What's the probability that xi is equal to 1? Okay, some of you solved this problem on a recent homework. And the way that you solve this is by asking the complement question. Okay, so you ask the question, what's the probability that it's empty? Okay, which is very easy to do, right? So usually that's the case because all the all the ball droppings are independent, right? So they multiply. Okay, so solution. Ask the complement question. What's the probability that bin I is empty? Okay, so what's the probability bin I is empty? Well, all the balls have to miss that bin. Okay, so the probability that a ball misses bin I is 1 minus 1 over m, right? Because it's 1 over m that's going to hit that bin, and 1 minus 1 over m that it misses that bin. And each ball is subject to that. So it's going to multiply, right? Like the independence applies, right? So it's just going to multiply kn times. That's how many balls there are. So we raise that to the kn. Okay, so this is by independence essentially. And then we use our standard trick, which is 1 plus x is roughly very close to e to the x. So this minus 1 over m is going to be part of an exponent. So e to the minus 1 over m, but we exponentiate that to kn. So this is kn over m. Okay, so I should probably do the wavy lines here. Okay, now, we could have taken a shortcut. Okay, you could also treat it this like a Poisson distribution. That's basically what's happened here. We're doing the exact same work we did before when we did the Poisson approximation. You know, what's the probability that bin I is empty, and we ended up with this quantity. Remember, it's 1 minus e to the minus lambda, where lambda is kn over m. That's the load factor, right? You have kn balls spread over m bins. Okay, so you can think of it that way. Think of it that way. Okay, let's tie this back into the bit vector. Okay, so in our problem, kn balls, these are our fingerprint hashes. The bins are bits in the bit vector, and each bin, or the probability xi is equal to 1, right? This is the probability that bit I is equal to 1. Now, if we want to use this coin flipping thing, or have something close to it, we would like that probability to be around a half. Okay? I think we might have done this, but I can't really remember. Anyway, we'll do it now. Okay, so we want the probability of AI equal 1 to be around a half. Okay, so we can just plug this in here. Okay, that would mean e to the minus kn over n is equal to a half. And we can take the natural log of both sides to get minus kn over m is equal to the natural log of a half. We'll just pause there for a second. Okay, so this looks like it's going to be bad news for m, like it's going to be a negative number, but take heart that if you take the natural log of anything that's less than 1, that's negative, actually. Okay, so just to spin this around, this negative will cancel out with this, and you get natural log of 2 as its cancellation. All right? Anyway, when we solve for m, we just cross multiply, and we end up with m is equal to kn divided by the natural log of 2. Okay, so as long as m is around this number, the probability of any bin being empty is going to be around a half, or non-empty. It's going to be around a half. Okay, so this is sort of another thing about how k and m and n are related. Okay, so keep that in mind for later. Next question, is xi independent of xj? So just to remind you what xi and xj are, xi is the event that bin I is non-empty, okay, it has a ball in it, versus xj, which is another bin, j has a ball in it, bin j has a ball in it. Are these two things independent? Maybe we should have a vote. We haven't done that in a while. You guys want to vote? Yeah, let's do it. I mean, you have a 50-50. Your probability is a half. I mean, the way I structure my vote, you can vote twice. Probability is 1, right? All right. Okay, so let's decide if these things are independent. Some of you did this homework problem, so you know the answer. That's okay. I like loaded dice. Okay, prepare to vote. Are these two things independent? You ready? Yeah? Okay, let's vote. Who thinks they're independent? Okay, who thinks they're not? Okay, most of you think they're not. That's true, they're not. Why are they not independent? Give me a reason. Good, yeah, a ball can't be, I couldn't have said it better, a ball couldn't be in both bins at the same time, right? So if a ball goes in bin I, it can't go in bin J, so the probability that bin J is empty or non-empty goes down, right? Yeah, great. Okay, so, but it's close, right? Because the probability when this gets large is actually, it goes down by just a little. Okay, so just a hedge. Okay, there's a slight negative correlation between these two things because when bin I, when a ball lands in bin I, it's slightly less likely bin J is not empty. Just can't be in two places at the same time. Okay, this is bad news for us in a way because it makes the analysis much harder. Okay, so if it was that they were independent, then we could just say, okay, well, it's very likely that all the bins sort of average out to be a probability of a half. So this is approximated by k coin tosses that are all independent. They are not independent coin tosses. We can't write that down. And that's sad because we would like to write that down. That's sort of the intuition. Okay, but because it's negatively correlated, it's actually skewed, like it's actually slightly less than a half, probably. It's way more likely anyway that it's going to be less than a half, if m is at least this number because of the negative correlation. And that's actually better than independence for our purposes. Okay, the inequality is going to go the correct direction. I am giving a simplified analysis of this because the actual analysis involves way more math than the course involves. Okay, but this negative correlation is good enough for our purposes. All right, so we'll see this on the next slide. Okay, so how do you choose m and k to make this scheme work? You choose them, well, you first pick k. Okay, so you first pick k, according to your error tolerance. Epsilon is usually it. So here's a simplified view. Okay, the probability of a false positive is equal to the probability that all of its fingerprint bits are 1. Okay, so it is the probability that that a of hash function I of x equals 1 for all i's. Okay, so this is going to go hash function 1 gives us 1, hash function 2 gives us 2, and hash function 3 and hash function k. Okay, so it's the intersection of all those events. Now, we would like to write that this is equal to the product of all of the probabilities of each one of these things individually being 1 due to independence, but we can't because they're not independent. But they're negatively correlated. Okay, so more or less, the products have got to be less than or equal to the AND event. Okay, because of the negative correlation. So we write less than or equal to this because of the negative correlation. Yeah, this is the simplification that I'm doing for today. Anyway, I hope you buy that. Anyway, the probability of a false positive, we can tune this to be less than or equal to 1 over 2 to the k. Okay, so how do we pick k? Well, we want this value to be less than or equal to our error tolerance. Okay, so since we want 1 over 2 to the k to be less than or equal to our stated error tolerance, we can cross multiply. Okay, so we get 2 to the k is greater than or equal to 1 over epsilon, and then take the log of both sides. Okay, so this would be k is at least as big as log base 2 of 1 over epsilon. Okay, so k is going to dictate the number of hash functions that we have. Okay, so we just find it according to this. And m, then we pick m to be according to what's over here. Okay, kn over natural log of 2. 1 over natural log of 2 is 1.44, approximately. Okay, so multiply by kn. Okay, so these are the two things. And these are all, so they're all rounded numbers, right? Because we can't have non-integers here. So we round this thing up to give us more space because we want more zeros. So this intuition says we want more zeros. Okay, and if we do this, then the probability will be roughly a half. It'll be slightly less than half. Okay, so to give you some examples of how big things, or actually how small things can get, k is equal to 7. We did earlier. Epsilon's less than 1%, which we saw earlier, and this gives us around 10 bits per key. Okay, which will cut, if it's a 32 bits per key sort of thing, it'll cut it by about a third. And strings, of course, will get cut even more. If you, I didn't really leave myself a lot of room here. If you wanted 0.1%, this would be around 15 bits per key. Okay, so 1 in 1,000 for false positive. And, in the short term, it ends up being a trade-off of about a factor of 10 for error for another 5 bits. Is sort of the space error trade-off. Okay, question? Yeah, so the bits per key is 1.44k, essentially. Yeah. So all the keys have to go in there. So it's going to scale by n, of course, and the number of bits is going to scale linearly in n. So this is the number here, 1.44k. No, bits per key is, the number of hash functions is k. The bits per key is, again, this is the number of bits, this is the whole size of the data structure, right here. Okay, m bits. So if you took this, m bits and divided it by n, that's the number of bits per key. Okay, so that's 1.44k. I don't think I satisfied you. You don't look happy, but okay, we'll come back around. Other questions? Is this cool? When I teach 225, I sort of go over this, but I don't do the analysis because I don't assume that you know anything about statistics. But you guys know some stuff, right? So this is good, right? So we see all of it. We see the balls in bins, or the Poisson thing coming in. Yeah? I think this is really cool. Anyway. Okay, last chance for questions. Okay, we got one more thing to do. And that's a little baby toe into the world of continuous random variables and distributions. Okay, let's say some words. Everything that you've been responsible for in this course deals with the discrete. That is a good thing because computers are discrete devices. They largely deal in integers. I mean, even real numbers, like doubles, they're an approximation for real numbers. They actually sort of cap out with some error tolerance. They get rounded at some point. So very, very rarely do you get an exact number. Anyway. Yeah, so that's good. That's good for computer scientists. Anyway, other statistics deals with continuous functions, and a lot of your calculus and other things you deal with continuous stuff. So there are a lot of good applications for discrete, but when you take the next course, I guess after this, Stat 271 I think is the next thing, they're going to deal with continuous stuff. And we haven't left you hanging or anything, but I just want you to not go in totally blind. Okay, so it's just a couple of lectures on this. Here's some themes. Every discrete distribution that you've seen has a continuous analog. Okay, and we'll focus on a couple of them as we go through. Anytime that you see a sum in a derivation, it gets replaced by an integral, and we'll see that in our first example. And you don't ask for a specific value, probability of a specific value. It turns out that the probability of spiking a specific value when drawn from a real number range is 0, which is maybe an oddity, considering what we've been doing, right? We roll a die. And, probability of 1, 2, 3, 4, 5, 6, those have actual probabilities. In real number land, the probability of that is 0. Instead, we ask for the probability of a range of numbers. Okay, so does this number belong to this range? And those are non-zero. Awesome. Okay, so let's dig into our first distribution, okay, which is uniform. Okay, so when we used to say the die roll thing, that's fine. But continuous random variables take on all possible values over an interval. And when we write the PDF, it's actually sort of a sum of things across that. It's an integral across those things. Okay, so here's the definition of PDF for continuous. Okay, so the probability density function is a function that maps numbers from plus and minus infinity everywhere in the real number line to non-negative values, such that if you sum everything up, and sums here are integrals, you end up getting a total of 1. Okay, so just some things that are the same and things that are different. We had probabilities before that were non-negative, but everything had to be between 0 and 1 before. Okay. This idea of adding everything up and it totals 1 is the same as it was before, but we're using an integral symbol instead. Okay, so here's your first PDF. Okay, so let u of x be 1/6 if it's in the range 0 to 6, 0 otherwise. So this is a piecewise curve. Let me plot it for you. Maybe I'll use the axes for red here, red for the axes. Okay, so here is 0. And as we trundle along, u of x is 0 until it gets to 0, and then it becomes a 6. So there's a step that goes up. Okay, so it's a 6th here, and this diagram's not to scale, but it'll go down to 0 again once you hit 6. Okay, so this thing between 0 and 6 has a non-zero probability density. Okay, so that's what u at x looks like. Okay, so the question is u of x a valid probability density function? Okay, so what this question is asking us to do is just verify that these conditions are met. Certainly this condition is met. It's non-negative, right? Everything is either a 6 through 0, so that's fine. So the only thing that we need to check is that the integral from minus infinity to infinity totals 1. Okay, so u of x is non-negative. Okay, so we're going to check the integral is equal to 1. Okay, so let's quickly do that. to really do this, or at least conceptually for me, is to break it up into its three pieces. Okay, so there's the bit that goes up to 0. There's the bit between 0 and 6. And there's the bit from 6 to infinity. But this ends up being 0, right? And that's 0. And the integral of 0 is just 0, so that's easy. So those go away. And this function here is 1/6. Okay, so that's a constant. And hopefully you remember how to integrate a constant. If not, I've got you, don't worry. Okay, so the integral of a constant is a linear term, right? Because the antiderivative, you know, pulling the power down and reducing this thing by 1, so the x disappears. Okay, so we evaluate this between 6 and 0, which is 6 over 6 minus 0 over 6, which is 1. Okay, so that's the other half of that. Okay, so that's our first definition. The next definition is, you know, what's probability over a range, and that's going to involve an integral as well. I'm not going to be able to get through that example. Okay, so I'm going to save that. That'll be our starting point for Friday. Okay, so thanks for listening. Let's get out of here. Yeah, see you there.